All right, what do we do? So let's assume that for now we won't make it into a function. Let's assume that we have a graph g, small letter g, that was created, and let's assume that let's make one step for now. So we have g, and let's set one node of g to sick, and let's do Gplot. Oh yeah, let's rerun it, like whichever. Let's run this one. Aha! Oh, look how fun. One node in the center became red. So if I run it again and again, nothing will happen, because the model was pre-generated before, and we just set one node to sick, and we don't have anything else. Okay, now let's define a probability. Probability p prob is good. Probability of spreading the disease, let's set it at 0.5 for now. This is a parameter, a hyperparameter of our model. Parameter, I guess. Okay. So let's write a loop. Before we do plot, for node in. So we have an option. We have two options here. How to deal with that? Because we should only consider sick nodes, right? We can ignore nodes that are healthy. Nothing to calculate there. But for each sick node, we should look at all healthy nodes that are connected to it and check whether the disease will jump. So either we have a list of all sick nodes, that's one option, or we go through all nodes and only do something for those that are sick. So let's opt for the second option now. It's actually slower than having a list, but let's code a slower version first, and then if you want to improve it, or maybe we'll have some space and time for that, like not today, but maybe later, I will show you some improvements how to make it run faster. But for now, let's code this brute force stupid solution. For node in G nodes, no, G nodes doesn't exist. Get nodes doesn't exist. For node in G get nodes, right? Print node. Am I doing it right? Yes. Okay, for node in G get nodes, if G values, so if this node is sick, if G values node equals 1, let's test it again. Print node is sick. Yes, only 0th node is sick for now. So time to propagate. We need to look at all nodes that are connected to this node. Neighbors are, how to get the neighbors? Well, we have a dictionary of all connections of each node. Gdict of node. So now neighbors is all connections of this node. Again, let's test that. Print neighbors. So we should have this red node, just in my case, seems to be connected to like 1, 2, 3, 4, 5 it appears. Yeah, 5. It's connected to 5 nodes, so we see these nodes. Good. By the way, see the numbers are small, which makes sense. They were added to this node early on in the development of the network. Good. So we have neighbors. Now we should loop through these neighbors. So we have loop inside a loop. I mean, we don't have to do that. We can also use NumPy and make it faster, but let's do a stupid brute force solution for now. For neighbor, that's a bad word to write. For neighbor in neighbors, time to toss a coin. if numpy random uniform, is it just 1? Okay, test time, and oops, and p random uniform, I can just use it without any arguments. Okay, uniform, if this thingy is below probability. So the idea is that uniform is anywhere, and we set the threshold, and only those that are below the threshold work. So if the probability is like 0.5, half of all uniforms will fall here, right? If the probability is lower, only this part will cause something to happen. So if a random number we just generated is below our probability threshold, then we need to connect them. No, we don't need to connect them. Then we make the node sick. Right. So G values neighbor equals 1, right? I think so. The only thing that we haven't done yet, we haven't checked, like there is no point in tossing a coin if the other node, if the neighboring node is already sick, but it should still work. It will just do some unnecessary work. Okay, let's run it once, because we don't have a loop over time yet. So after 1, oh no, that's a mistake. Uh-oh. Oh, right. Of course, silly me. See what happened? We kind of... I started changing... Oh, Lord. So embarrassing. I started changing node status as I was going through the loop. So what happened is that disease propagated, and then I visited this node, and oh, it's actually sick now, and I propagated the disease once again. One more node was included into sick once, and some of those were nodes already visited in the loop and they didn't affect the calculation, but some of them were nodes that were only in the queue that were due to be visited, and so they were healthy when the loop had started, but by the time I visited them, they were sick already. So we don't want to do that, because while the disease, like, it does propagate, we have no control. It's not like we don't have the time frame structure. We don't have this moment when like a day has passed, and we want that. So we need to do a different thing. We need to mark them as like to be infected, and then once the day is over, we just make them all infected. All right, good. So this is not happening. We'll have a list of infected. Infected, append a neighbor, and we'll add infected as a list, and this list will be empty, and we'll do it in the very beginning. Infected is an empty list. And once we're done, once we decided which nodes are infected, we'll have a list of infected nodes. So let's start with testing that. We have to rerun this thing, or maybe we drop. Okay, let me write a tiny cell here. Let me just set all nodes to healthy. For node in G get nodes, G values node equals 0. This will set all nodes to healthy, so that I could restart it. Sets all nodes to healthy. And then I run this thing. Okay, so back in time, only one node is sick. 4 nodes are on the list, over the infected list. If I rerun it, sometimes it's only 2, sometimes it's only 1, again 2. So it seems to be working, right? Okay, so we have the list of nodes to be infected, and now for node in infected, G values node equals 1. Right? So first we calculate this part. This part calculates which nodes are to be infected, will get infected by the end of the day. And here, like Mafia game or Salem, I think it's called here, right? Like the night had come. Infected nodes become sick. So let's try that. Let's try to run this several times. After one run, one node is infected. After 2 runs, like a few more are infected. Oh, that was weird. On this particular case, all of them got infected. I don't like that. What? Oh, right. Actually, yeah, the first step happens immediately. So after running it once, we have the results of first infection. So on day 1, so we start with only node 0 infected, but by the end of day 1, a few of its neighbors are infected. We run it again, more infected. We run it again, even more infected. And if we run it several times in a row, you can see how the disease spreads. It stops spreading. No, what? Okay, yeah, it's totally spreads through the community. It just takes a while to reach some of the neighbors because it's toss coin at every step. Good. Are we ready to add time? I'm guessing so. So we can add time, and what will be our output? We can look at the number of nodes that are infected, maybe, right? So let's do that. Let's make it a function. Define pandemic. Pandemic gets a few parameters. It gets the parameter, it gets the few arguments. It gets the graph, right? It gets the probability, and let's set half as the default value, but it doesn't have to be half. And steps, how many steps to run, like what is the default? 10. Should we include this part that sets all of them to healthy? Yeah, let's include this part as well. Okay. The global description runs the pandemic for several steps. So first set all nodes to healthy. Only node 0 is sick, and then we go through this thing. And at the end, we don't even have to. Oh yeah, we want to return something. Return history. History is not defined yet. We don't have to return the object, the graph, because actually it messes with it. So when this function runs, it messes with the graph, and so we don't have to return it. It will be different after the function had run. But we probably want to count the number of nodes that was sick at any point, because it will give us some readout. And later, when we look at, like, when we compare the networks, we can make some nice plots. They won't actually look like that. For now, they will look like that. They are only growing because the number of people, because the people never recover for now. But okay, at least it's some plot. So we need to add the calculation of this plot somewhere. Let's yeah, and we need to add a loop over time. So let's add that. Let's start with the loop over time. Infected infected is actually newly infected. Let's rename it newly infected. Newly infected, done. Because if we have a good variable name, we don't have to add a comment. For t in range and steps, t for time, all of that moves into this time loop, and now we need to add history. History equals np. I want it to be numpy because it's just numbers. Numpy 0 zeros and steps, and what's the easiest way to calculate the total number? Oh, you know what? Let's do new cases. Let's do new cases, because that's something that we have seen recently a lot in the news, and it's so easy to calculate because we have this newly infected list. So the length of this list is the new cases every day. So history on the day t is just the length of newly infected. But obviously you can change it into the total number of cases if you want to, or we can just do it later. So okay, return history. So how does it work now? We do pandemic g. We can give like some of the parameters. Probability equals 0.5 and steps equals 10, and we want to save it into history, and we do Gplot. Let's make something Gplot. Well, let's keep it like that for now. Does it run? Yep. Okay. So do we have different plots? Yeah, we have slightly different plots. Let's just test it a little bit. What if probability is smaller? Okay, we have less propagation. Look at that. What if probability is like really, really large, 0.99? Uh-oh, everybody is sick. Okay, good, that works. What if probability is really small, but the number of steps is really large? So we have 100 steps. Yep, it works. Everyone is sick. Good. So let's go back. Let's actually keep that. Let's keep a fairly small probability, but lots of steps. Let's plot that. So let's be pretty. PLT figure. No, we don't need PLT figure. PLT subplot 1-to-1 Gplot. No, we don't need PLT figure. Okay, just a second. PLT subplot 1-to-2, so it will be the second plot. Plot history. We need a figure because we want it to be elongated so that two plots wouldn't look ridiculous. Figure fixed size equals, what was my favorite? 12 by 4, I think. Okay, something didn't work. Because plot doesn't work, we need to do PLT plot. Oh. That's wrong. Right? Can you see that? That's wrong. What's wrong about it? The number of cases never goes down, but it should go down. Where did I screw up? For some reason. Oh, right. So number of new cases never goes down. Why? Even though all of them are infected? Because I never check whether the neighbor that got the disease already has it. Remember, back like a few minutes ago, I said that it would still work. But actually now we no longer can tolerate that. So here, when we go through neighbors, when we create neighbors, either here, when we create neighbors, we may want to filter them somehow and only look at those that are still healthy, or here actually. Let's do it here. Well, should we do it here? We'll still have to toss a die. It's okay. It's all right. We can optimize it later. We can make it much faster if we want to, but we're doing none of the tricks to make it fast for now. We're just doing a really straightforward thing. If what? If it's healthy. So it's called neighbor. If it's healthy, which means if G values neighbor healthy have the value of 0. If it's 0, if its value is 0 and the token cost or the die roll gives us the probability, then infected. Otherwise, don't bother. Aha! Nice. Yep. Now it looks like something. The cases grow, and it's kind of noisy here because the probability of propagation is low. We can go back to like 0.5 and 10 steps if you wish. Okay, let's do 20 steps. Let's do 30 steps. Yeah, so cases grow and then they go down because the entire population is now infected. Right? Good. We achieved a milestone that we have a working model now. We have a working model and we have an output. Let me add some pretty, what is that? PLT plot, PLT X label a day, PLT Y label, and new cases. Suppress. Right, good. Awesome. Homework. Like originally, in my original plan, I planned in my original plan, I said for the day, think of computational experiment, how to run computational experiments, what hyperparameters to change. Okay, it looks like we'll have to wait a little bit with this one, but let's do the first step in this direction, and then we'll do a little bit more later. So homework is after you implement all of that, not messing with the parameters too much. Let's compare the two networks. We have two networks. So let's run the disease on one network, and let's run the disease on the other network. And we'll get the new cases over time for both networks, and let's see which network is more susceptible. Okay, let me write that down, otherwise we'll both forget. Homework. Compare two network configurations. Run the pandemic on both of them and compare the plots of new cases. Right? For now, keep everything else the same. The number of nodes, edges, probability of spread, contagion. Keep everything else the same, right? So what else do we want to do? Each individual run is quite noisy, all right? So add a loop and averaging to run. Add a loop and averaging to run several experiments for both network types. What do I mean by several experiments? We have two sources of randomness actually. One source of randomness is how the disease runs, because we have probability involved, but the other one is the network itself. I kept reusing the same network here, but we can recalculate new networks. So I want you to do both. For now, like both of them together without separating them. Add a loop and averaging to run several experiments for both network types. Like, meaning for each network type, generate n different networks and run a pandemics on each of them. Remember the curves, average the curves, and plot these smooth averages. Does make sense? So we want to have a loop for experiments. So we want to pick a network type, and then we want to repeat, like, make a network, run a pandemics, make a network, run a pandemics, make a network, run a pandemics, and pandemic. And every time, so network, pandemic, every time we save the curve, and each curve will be noisy, but then you average all of these curves, and you have a like smooth curve for this type of network, for this size of the network, for this probability of spreading. We actually did something like that back in February or March, I don't remember. We had an exercise when we had a model that generated something noisy, and we averaged lots of noisy curves and made one or two. In this case, we also will have two nice smooth curves. So that's what we want. One tiny thing, so that's the biggest part. It's not hard, it's just annoying because you need to actually write that, but you can do that, I believe in you. And one part that's like a little part that I haven't done, don't always infect, like when running pandemic, don't always infect the same node number 0, because node number 0, it's not special in one type of a network, but it is special in this other. In this other, the node type number 0 is the first node to appear, so actually it's very well connected, right? It's always this node somewhere in the middle, which means that if we always pick node number 0, it's not actually fair. It's as if like the king of the country is always we're always the first to get sick, which is not necessarily true. Maybe it's one of those like poorly connected nodes that get sick. So when running pandemic, don't always infect the same node, but pick the patient 0 at random among all nodes in the network, right? Let's move it upwards. We need to actually, you'll need to implement that first, and then you can do the other two exercises. Right, so do that. You should have two plots, and actually, okay, let's add one more little thing. Make a guess for yourself. Which type of a network of two we have so far will be more prone to pandemic? So which one of those is more susceptible? Which one of those is riskier? Which one of those two societies is riskier? Make a guess, then model it and check whether your guess was right. Okay? All right. I think that sounds like a good point, and we'll talk about that during our next meeting. Good luck.